This is going to be a brief video lesson on section 8.2 titled Apply Exponent Properties Involving Quotients. It's very similar to 8.1, so I would suggest that you make sure to watch that video first and understand that section first in order to better understand 8.2. So 8.2 starts off in a similar fashion as 8.1. One of the things you have to keep in mind when dealing with products or quotients involving exponents, the bases have to be the same. So the same rule applies to 8.2, which deals with quotients. So let's start with this example. A to the fifth power divided by a to the second power. So here we have a quotient. We have a pair of exponential forms being divided. A to the fifth divided by a to the second. So one way that we can write this out is a to the fifth means multiply a against itself 5 times. So a times a times a times a times a. On the bottom we have a to the second power, or a squared, which means a multiplied against itself twice. So once you do this, you will see that you can simplify this expression by crossing off identical values from the numerator and the denominator. So here I have an a and an a. I can cross those out. I have another a and another a. I can cross those out. So now on the bottom I have no more a's, but on the top I still have 3 a's being multiplied against each other. So that's a to the third on the top and nothing on the bottom. So in essence what I did is I subtracted 5 minus 2, just the exponents, which gave me that a to the third. So this is obviously the long way of doing it, and it becomes a little unwieldy to do for most problems we'll encounter. So you want to use the shortcut, which says to divide powers having the same base, and they have the same base, subtract the exponents. So you subtract 5 minus 2, so you subtract 2 from 5 and you get a to the third for that particular problem. So that's what you do when you have, again, a pair of exponential forms being divided. This isn't the complete answer yet. A equals to a third, but you also have to write down that a is not equal to 0. Now why would we want to do that? Because if a was ever equal to a 0, you would have a 0 in the denominator. And if you remember, I told you, and we actually went over in one of the sections, that you cannot divide by 0. It breaks a few rules in math, so just simply can't happen. So whenever you have variables for bases and you're dividing, whatever variables in the denominator, you have to specify that it cannot equal to 0. So that's the full answer to that problem. Let's do an example. Let's do this particular example. X to the seventh divided by x to the third. So again, very similar to the problem we just did. You have a pair of exponential forms. They're being divided and they have the same base, so we can work with them. So it's going to be x, the base is the same, 7 minus 3 for the exponents, which is x to the fourth power, 7 minus 3. But you do have to specify that x cannot possibly equal to 0 ever in this case, because dividing by 0, well, again, it's a no solution. Alright, let's do one more. Actually, let's do 2 more. Here's another example. I have 5 to the 10th power divided by 5 to the 6th power. Again, similar to what we did before. We have a pair of exponential forms and they're being divided. The base is the same, so we can work with them. We rewrite the base here, and the exponents we subtract the bottom from top, 10 minus 6, which equals to 5 to the 4th power. Now here I don't have to write down 5 can't equal to 4 because it's a 5. Obviously it's not, I'm sorry, 5 can't equal to a 0, so we're going to have to write this down for this. A 5 can't be a 0. It's not a variable, it's a constant. 5 is a 5. So that particular step you can skip for any base that is a constant. Let's do one more here to save some space. I'll box this one out. We have x to the third power times y all over x to the second power. So it looks a little different, right? But treat it as what we just did. The y doesn't have a corresponding base in the denominator, which means we really can't do anything with it. So you just write the y over here. That base isn't going to change. The x, on the other hand, you have an x to the numerator and an x to the denominator, so the same basis, we can work with that. And then you write that down as x 3 minus 2, which equals to x to the first times y, and you don't have to write, the exponent to the first power, so x times y. But you're not finished, because x is in the denominator and x can never be equal to 0. You also have to say that x cannot equal to a 0. So that would be your full answer for that particular problem. So if you had more than a single variable, for example, if I had a y in the denominator and that y remained in the denominator after we did our math, you would have to specify over here that y also can't be a 0. So whatever variable is in the denominator, you have to specify for it that you cannot have that variable be equal to a 0. So that was the quotient of powers. So again, to divide powers having the same base, you subtract the exponents like we did over here. So next up, we are going to do something a little bit different, not very different, but just a little bit different. We're going to talk about the power of a quotient. So what does that mean? To find the power of a quotient, you find the power of the numerator and the power of the denominator, and then you divide. So for example, you have 3 over 2, so that's a quotient, all raised to the 7th power. So 3 over 2, that's your base, all raised to the 7th power. So what does that equal to? Well, this is very similar to the power of a power, where you would distribute the exponent that's outside to the exponents that are inside. In here, both the 3 and the 2 have a hidden exponent of 1. So you would distribute the 7 to both the 3 and the exponent of the 3 and the exponent of the 2, which is 1 in both cases. So 1 times 7 is a 7. So you would get 3 to the 7th power over 2 to the 7th power. And you stop right there. You can't do anything else because the two exponent forms have different bases, a 3 and a 2, which means you're done. That's your answer. Let's do another example. Let's take a look at this problem right here. 5 over 6 all squared. Just like before, this is a power of a quotient, which is very similar to the power of a power. Each of the bases here, the one in the numerator and the one in the denominator, the 5 and the 6, have a hidden exponent of 1. That's not written. So you have to distribute the 2 to both of these exponents. 2 times 1 is 2, 2 times 1 is 2, so 5 squared over 6 squared. And you can leave it in this particular form. Obviously, you could have solved this one out. This was an easy solution, 25 over 36, but you don't have to. So you can leave it in this form. Can't do anything to the exponents because the bases are different. Let's do one that's a tad bit different, just a little bit. What if we have negative 2 to the third? Oh, sorry, negative 2 over 3 all raised to the third, or cubed. Again, this is very similar to what we have done so far, but this negative here doesn't apply to both the numerator and the denominator. It applies either to the numerator or the denominator. In reality, it makes no difference, but the convention is to write the negative with the numerator if you have to choose. So again, a lot of times it's left in the middle, but you have to choose which one to apply to, because it doesn't apply to both per se. It's not a -2 over a -3. It's a -2 over 3. But you have to choose to apply to one, you apply it to the numerator. So I just rewrote this, literally. And now you do the same thing with it over there. -2 has an exponent of 1, the -3 has an exponent of 1, and then you just go ahead and multiply them, the exponents. So you get -2 to, I'm sorry, that was a third, to the third power over 3 to the third power. So not very different. All we did was we rewrote the value here with the fraction, with the negative jumping up to the numerator. Again, it can go to the denominator as well as just, so you could have had a -3 cubed instead and had a +2 to cubed up top. But the convention is to move the sign up top. You don't want the negative in the denominator if you can help it. Alright, one that's just a bit more complicated. Not much, but just a little bit. So we have 4x squared over 5y all raised to the third power. Now this is kind of like combining our power to the power problems and the power of a quotient problems all in one. So the exponent 3 that's outside here, it's an external power, has to be distributed to every single internal exponent multiplied. So if there are any invisible exponents or not visible ones, you have to show them. So the 4 has an exponent of 1, the base 5 is an exponent of 1, the base y is an exponent of 1, and the x already has the squared exponent present. So you have to distribute this to every single exponent that's internal. So you're going to get 4 to the third because 1 times 3 is 3. Then x to the sixth because 2 times 3 is 6, over 5 to the third because 1 times 3 is 3, and y to the third, again 1 times 3 is 3. And you're done. There's really not much else to do. Obviously you could have worked out the 4 cubed and the 5 cubed, but you're not asked to do this. So that is really it for 8.2. I'm going to do a video lesson of the homework problems, and there's going to be some more complicated problems on the homework, and on my video I'll make sure to do a few of those, but this was kind of like the basics. So watch this first if you're confused about 8.2, and then try the homework, and then watch my homework video as well for some additional help. So thank you very much for watching, and have a nice day.